Hello guys, today we are going to look into a topic that deals with Palmprint biometric for security of hardware IPs. This work was presented in 7th IEEE ISIS and the extended version of the work was published in IEEE Transactions on Consumer Electronics. Let's look into some of the background information. So digital signal processing IPs are integrated into the consumer electronic systems to perform tasks that are based on images, audios, and video processing. These are usually data intensive or data crunching applications which require higher efficacy and low cost. However, due to the involvement of multiple offshore entities during the globalization of the integrated circuit design supply chain, uh, certain serious hardware threats of IP piracy or IP counterfeiting has cropped up. Counterfeited IPs could mean that they have malicious logic like Trojans inside them, and these Trojans could be very erratic and unreliable by nature and highly unsafe for an end consumer. So, before being integrated into the consumer electronic systems, it is imperative that some sort of detection or checks are performed to find out which is an authentic and which is a fake version of the IP. In this discussion today, we are going to focus on how the Palmprint biometric is capable of generating non-replicable, non-vulnerable secret biometric information represented or converted as digital watermark and embedded into the IP designs. Let's look into some of the literature review work. So, hardware security field has produced a lot of important works like hardware steganography, hardware watermarking, fingerprint biometric based hardware security. All of these techniques are used for detecting fraud IP ownership or IP piracy or pirated IP detection process. So, for example, the hardware steganography technique that is used to address the IP counterfeiting problem, they suffer from some inherent drawbacks like, for example, if the encoding rules or the secret parameter values like entropy threshold they get leaked to an adversary, then the secret stegomark becomes highly vulnerable. The traditional watermarking approaches, for example, the ones that have been based on the signature-based schemes of the IP vendor directly, they rely on digital encoding techniques and watermark constraint strength. So if these information are replicated or leaked, then it could be reused and unauthorized watermark generation can be possible. In one of the recent works on fingerprint biometric, which is the work from my own group, we have proposed fingerprint biometric to perform IP protection process. However, fingerprint biometric also has some problems. Like for example, it is not purely contactless, and secondly, there are requirement of specific pre-processing algorithms for enhancement of the extracted minutia point information. Like for example, if the minutia point information like ridges are broken, then it needs to be subjected to certain algorithms to enhance that information. So all these leads to extra complexity, and finally it also gets affected by external environmental factors like dirt and grease when the fingerprint biometric is being captured through an optical scanner for the first time. The Palmprint biometric, on the other hand, it in short produces specific nodal points from the palm image after extraction or after capturing, and then that gets implanted into the DSP IPs for for being as one of the authentic IP versions into the C systems. Let's see how the algorithm works. The first step is to capture the palmprint biometric with grid size and spacing. Okay, and that is done using the vendor's palmprint. Second, it derives the nodal points on the palm image, assigns a naming convention. Finally, it produces the image with the palmprint features, followed by detection and determination of the feature dimensions between the nodal points for selected palm features, and it decides the feature order based on the information provided by the IP vendor for concatenation of all those information. Once it is done, then it gets converted into its respective palmprint signature for being converted into its secret security constraints using encoding rules, which then gets embedded into the HLS framework of the IP design process while the register allocation phase is being going on. and ultimately it results into an RTL data path of the DSP coprocessor. So this is the captured palm image, and this is laid out in terms of specific grid size and spacing. And these are the different feature sets of the palm image. For example, these are the abbreviated names: TATF, DSF, DFF, and so on. So there are in total 19 palm print features that have been exploited in order to generate the palm print signature. And these are the different nodal points that are indicating the start and end of that specific palm print feature. These nodal points are used to compute the feature dimensions, and once those feature dimensions are computed, then it gets converted into its respective binary representation that has 3 unique characters: 1, 0, and binary dot. As you can see, there are 19 features in totality here. The details of all these features are provided in the respective research paper, so interested readers would please refer to that to find out more details. Now, once these 3 unique characters are found out, then we try to devise an embedding rule for that. So for example, bit 1 would embed an edge between node pair or dot, 0 would embed an edge between node pair even, dot would embed a edge pair between 0 integer into the colored interval graph or registry allocation phase of the target DSP design. So for example, 0 integer could be T0, T2, T0, T4 and so on. So T refers to the storage variable here. So we are referring to storage variables within the scheduling graph of the design with the help of variable T here. And or dot would mean it could be, for example, T1, T3, T27, T29 and so on. All of these storage variable pairs have to be satisfied into the register allocation phase. Okay, so for example, T0, T2 would be assigned to different registers, T0, T4 would be assigned to different registers and so on. That would mean that whenever you have a storage variable pair, they are forced to be executed using different distinct registers and not through the same register. That's how this entire register allocation table gets satisfied with the help of these security constraints derived from the Palmprint signature. The security analysis is performed in terms of probability of coincidence and tamper tolerance metric, which are standard metrics used in the literature. And we have found out that the probability of coincidence of our approach, which is blue line here, is lower than 5 and 8. 5 is the one from IP steganography, 8 is one from fingerprint biometric, which means that the watermark collision chances are low, and tamper tolerance means that it is having greater tolerance to brute force attack or any sort of tampering attack like watermark removal or watermark tampering, and that is only possible when you have a larger signature space like the proposed approach. So TT of the proposed approach is therefore larger compared to it. The design cost analysis reveals that the cost overhead is significantly nominal compared to its baseline, and therefore this is a very acceptable design cost overhead. The concluding statement would be that the proposed work has presented a contactless Palmprint biometric that is able to distinguish between authentic and fake IP versions, and it's non-replicable and non-vulnerable by nature, as it offers several security layers like the Palmprint information of the IP vendor, followed by the different Palmprint feature sets, the concatenation order, the encoding rule. All of these layers have to be bypassed or broken by the attacker in order to regenerate the exact Palmprint signature for false claim of IP ownership or for evading IP detection process. These are the two techniques on which this has been compared with approach 5 and approach 8. Thank you.